Now, we skip section 2 of chapter 10, so we're jumping right into what is called exponential functions. And as you probably can realize from the title, it's functions that the variable is the exponent. So let's take a look at that. These are the many objectives that we'll be moving through. You don't have to write these down, but things that we will cover. If you want to read them, you can. Let's move on. Now, I'm going to give you some background on this, and let me set it up, and I want you to copy this in your notes as well. So we'll do this in parts. Keep in mind that anytime you see f of x, as is written here, this is the symbol for function, and that our exponent here is the x. So this is where we're going to put different values, and we're going to make a little t-chart. Now keep in mind that f of x can always be replaced with a y from our old lessons here of graphing. So this is as much as you should copy down now, and then in a few moments I'll give you something else. So now we want you to fill these t-charts in with 0, 1, 2, 3, negative 1, negative 2, because we will be asking you to graph this. Okay? So pause and do this. Now, the first one we're going to do is f of x. We're going to substitute, since you can't have a 1 for this. They have to be numbers greater than 0. But we're not going to use fractions yet, but we'll start with numbers where b is not a 1. But let's say b could be, let's say, a 2. This is a nice easy one. And then we're going to have it to some exponent. And then here we're going to do f of x, where our b value is a 4. So these are two specific examples we're doing as we look at what happens when we have an exponential function. Now remember, b here cannot be a 1, but it could be a 2. And I've just picked some numbers for an example. Okay, so we now are going to substitute for our exponent here a 0. So 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Now if we put a negative 1 there, let me show you that up here. 2 to the negative 1, you might recall from earlier lessons, we just take the 2 down to the denominator, and it becomes 2 to the first. So when we take 2 to the negative 1, it's just the reciprocal of 2, which is 1/2. And this one becomes 2 to the negative 2, which is 1 over 2 to the second, which is the reciprocal of 4, which is 1/4. So this gives us some values. Now let's do it for this one here as well. So 4 to the 0 power, anything to the 0 power is 1. 4 to the first power is 4. 4 to the second power is 16. 4 to the third power is 64. So you see these numbers get quite large. This is referred to as exponential growth. Now, again, 4 to the negative 1 is just the reciprocal of 4, 1/4. 4 to the negative 2 is 1 over 4 to the second, so the reciprocal of that, which is 1/16. So now we have some points for plotting. Now what we'd like you to do is make a little graph here. Now we only need the upper parts of a graph. So we're going to plot these, and I'll set it up to save a little time here. So now we're going to plot these points that we have. So when x is 0 for this one, y is 1. When it's 1, y is 2. When it's 2, y is 4. And when it's 3, y is 8. So I'm just going to sketch this now. This line is not straight. And it goes on like so. Now, how about when x is a negative 1? Negative 1, y is 1/2. And when x is a negative 2, y is 1/4. So this looks like so. So this is the typical curve for exponential function. And we're looking at here b is 2 to the x power. And it looks like so. Now how about when b is 4? 4 to the x power. Well, what happens? Well, we'll plot this. Again, when x is 0, 4 to the 0 power is 1. Anything to the 0 power is 1. So notice these 2 points are the same. And then when it's 1, this goes up to 4. So instead of being 2, the line's going in a little closer. And then when we get 2, this goes way up there to 16. That is no longer on the graph, and I'm off of the graph. Now let me show you in red. If I put this on that same graph. So again, it's 0, but it's 2, and then it's 4, and then it's 8. I'm a little bit off there. Let's move this point in a little closer there. So you see the difference. This line is out here, while the other, this line is in here. So as these numbers get bigger, 2, our b is 2, our b is 4, this curve gets closer to the y-axis, and that's a kind of a trait. And then down here, the blue would be 1/4, so really close, and then 1/16, a little closer to this side. So again, this is some background, and we spent almost 10 minutes on this to give you an idea of what's happening as we do exponential functions. And then here, they're giving us some more background on if we have a negative exponent, that just turns it into the reciprocal of 2. That's where we get our 1/2. So there are fractions in here, and they're giving us some background here. Now, when we have negative values, this is actually a decay function. When our x value itself is a negative. This is a decay function. So keep that in mind. So they're giving us some general functions. Remember, b to a 0 power is always 1. So that is basically our y-intercept. And I need to point out one other thing here. Now, you don't need a new picture of this. You can go back to the graph you did on the previous slides. This is f of x equals 2 to the x power. So as it goes up here, this is our basic curve, but then our 1/2 here, you recall, was there. If x is a -1, it's 1/2. If x is a -2, it's 1/4. And I can't draw this very well. But this line, as it goes on the left side of quadrant 2, you may recall, gets closer and closer to the x-axis, but it never reaches the x-axis. We call this, for the negative values of x, the x-axis, that is, the value that this curve gets closer and closer to, but never touches. We call the x-axis, you need to write this down, the horizontal asymptote. And what is an asymptote? It's a value that something gets close to, but never reaches it. And that's the horizontal asymptote. And what is the horizontal asymptote in these values that we're doing? And the answer is, it is the the x-axis. This x-axis here. That is your horizontal asymptote. Okay, I should have included that in the other slide, but I see they're featuring it here, and we want to give you these words for your vocabulary. It's a line that the values get closer and closer to, but never reach it. And what does it never reach here? The x-axis. The x-axis is the horizontal asymptote. Okay. Now, for our first example, we're going to read this over carefully. And we have 10,000 bacteria present when the time is 0. That is the start. And this is the function for the growth of bacteria. Now, they didn't put it in this function symbol. They're just using the word function of y equals y sub 0. Now, the sub 0 only indicates the start of it, and then it's going to be multiplied by 2, and then this is your exponent, where we're including the t as a time factor. So we do some substitution. At the beginning of the experiment, how many bacteria do you have? Well, you have 10,000. You're going to multiply. Now remember, you always do the exponent part first. So I'm going to put this in a parenthesis here and say this is going to be 2 to 0.5. And they want to know for our time in 1 day. Well, remember, we're measuring this in hours. So how many hours in a day? And the answer is 24. So as we put this in our calculator, the first thing you're going to put in there is the 2 caret, and just put this in parentheses, 0.5 times, putting that up a little higher, 24, close parentheses, hit enter. That'll give you a value on your calculator. And now you put in the 10,000. And it's going to give you your answer here. So as we follow the book, our time, our t is 24. Y to the sub-0 is 10,000. And again, times 2. We have to do this part, the exponent, first in our order of operations. So when we take half of 24, we get a 12. So in a sense, 2 to the 12th power, and that gives you this value that you're now going to multiply by 10,000, and it gives you this. So you see, bacteria that grow exponentially become quite a large population in a day. When I taught biology, we would do this, and we would measure cloudiness of the solution, and we had a photospectrometer that we can shine a light through, and then we worked out some interesting things. Okay, that's example A. Now, putting this in scientific notation, you're going to move your decimal point. Let's just review that. From here, I'm going to make this a number between 1 and 10. So 1, 2, 3, 4, 5, 6, 7. So it's a number between 1 and 10 times some power of 10. And the number of decimal places we move it over, that's our exponent. And the number between 1 and 10 that we get is 4.096. And that's how they get this answer. Okay, let's go on. Now they're showing you if you just put this into your calculator, it doesn't have to be a TI-84, because we're not graphing here. Again, caret, this, and the TIAs in the calculators know they have to do the exponent first. Then you multiply by 10,000 and you get this. Okay. Now, here we're going to use the formula for exponential growth, which is this, which we just had here, to determine the exponential function that fits the following information. So we're starting with 5,000 bacteria, and after 3 days, we're going to have this many. So we have to try to find our variable here. So taking the information they've given us so far, we have our function of y at the beginning, b to the t power. And we know that we started now with this, well, we started with the 5,000, so we put the 5,000 there. We know we're going to end up with this. And we're saying 3 days now. So we're going to have our time, instead of being hours, will be days. So we put our exponent of 3. So what do we do now? Well, it's just solving this equation. We're going to divide both sides by 5,000. Here the 5,000s cancel out, and we get b to the third, and we get an answer here. And then how do we find out what b is from an earlier lesson? Well, we take the cube root of this side, and we'll take the cube root of that side, And that will leave us with B, and then our answer here. All right, so not too bad. Again, understanding the formula. And when I taught biology again, we did lots of culturing with our agar and petri dishes. This looks like a blood agar that they're having here, which is very good for pathogens growing. So what do you think we're going to do here? We're going to divide both sides by 5,000. And when we do that, we get 27. And when we take the cube root of B and the cube root of 27, we get B equals 3. So what will our formula be? Well, the function of y is, and this was y sub 0, our initial amount, 5,000, and our B value now we know is 3. Okay. So again, in your practice and certification, you're going to get examples like this. And now we have a number of tools in our toolkit. Now, we are at 20 minutes, and we're going into what is called compound interest. So I will definitely do this one in 2 parts, because we have quite a bit to look at, and we don't want to keep it too long.